presentation of today. Okay, it's Lustre client encryption, very interesting topic from Sébastien Buisson. Welcome, Whamcloud, I'm sorry. Sébastien has been working with Lustre for over a decade, initially solution and development activities for Pro, but in recent years focusing on Lustre development at DDN. He is a recognized expert in the areas of Lustre security within the Lustre community and has presented various topics on in this area at Lustre conferences over the years. He currently works on the Whamcloud engineering division at DDN and is based in Grenoble, France. So welcome, Sébastien.
Thank you. Hi, everyone. So let me share my screen. Okay. Hopefully you can see my slides. So let's see. Okay, here we go. So the need for end-to-end and at-rest encryption is drawing more and more attention today. In Lustre, we have implemented encryption directly at the Lustre client level. As a benefit, files transferred between clients and servers are encrypted, as well as files stored on persistent storage on server side. So here is the outline for today. First, a quick reminder about what is encryption for Lustre. Then I will give details about the encryption feature that is available in the new Lustre 2.14 release. And then I will explain the remaining work currently in progress. Okay, let's get started. So the use case we want to address is to provide a special directory for each user to safely store sensitive files. We have two goals. The first one is to protect files in transit between clients and servers. And the second goal is to protect files at rest. The solution retained relies on FScript on kernel side. And its core principle is that pages in the page cache always contain clear text data. On user space, we rely on the FScript user space tool. And this tool is used to decide which directories to encrypt and how. So what is available with the new Lustre 2.14 release? We are providing the ability to encrypt file content, which means we encrypt on write and we decrypt on read. And we are providing the ability to set encryption policies on directories. That means we support new IO controls that are sent by the FScript user space tool. Please remember that in 2.14, we do not provide encryption of file and directory names. So in new 2.14 release, encryption support is built by default via the embedded LLcrypt library that is included inside libcfs. So basically, we had to copy FScript from Linux 5.4 and include that inside the Lustre tree. The reason is we need to support content encryption mode. And you can benefit from client encryption as soon as your client runs on the following distributions. So CentOS or Red Hat 5.1 or later, Ubuntu 18.04 or later, and SLES 15 SP2 or later. The encryption modes that we support are directly imposed by FScript. So this is AES 256 for content and null for name encryption, because this is 2.14 release, and or AES 128 for content and null for file names. You can have a look at the Lustre Operations Manual, chapter 30.5. There's plenty of documentation there about access semantic, threat model, and key hierarchy as well. So a quick word about key hierarchy. When you decide to encrypt a directory, a master key is generated and used to protect the directory. But no file is actually encrypted with that master key. In fact, each file is encrypted with its own key that is derived from the master key using a nonce. And this nonce is randomly generated and stored inside an extended attribute of the file. Lustre 2.14 supports new I controls, giving the ability to associate encryption policies to directories. But concretely, how to tell which directories to encrypt and how? Well, thanks to the FSCrypt user space tool. Here I have listed the main FSCrypt commands, but I propose to go for a demo to illustrate how it works. So please make sure to enable full screen mode so that you can watch the demo comfortably. Let me share my terminal. All right. Hopefully you are able to see a console. Okay, so this is a pre-recorded demo that I am going to comment live. This demo is run as a regular user named user 0. And we are running on a CentOS 8.3 node with a 4.18 kernel. So this is a Lustre client on which I am mounting Lustre. This is a simple file system made of 2 MDTs and 2 OSTs. And we are running Lustre 2.14.0. So let's create first a directory for this user and grant him access rights. So the first thing to do is to set up FSCrypt. So this is the only command that for which you need root access. FSCrypt setup is going to create configuration files locally in your node. So this is typically the command that you would run on every client node. After that, you need to run FSCrypt setup with the Lustre mount point, and this is going to create metadata required by FSCrypt. So this command needs to be run only once. Now let's create a directory named Vault and decide to encrypt these directories. For that, you need to choose a protector. So here we choose a custom passphrase and we input the passphrase. Okay, so now we can write to files, we can create directories and so forth. We can read from files and everything here is encrypted. We do support direct IO on encrypted files. So here I'm writing 1 megabyte in an encrypted file in ODirect. We do support truncate on encrypted files. We do support mmap on encrypted files. Remember, this is because the page cache contains clear text data. We do support holes in encrypted files. So here I am writing 1 megabyte at offset 10 megabyte, and with file frag, we can check that only 1 megabyte was actually allocated at the 10 megabyte offset. We do support data on MDT with encrypted files. So here I'm creating a DOM layout. And let me write 4 kilobytes at the beginning of the file. Here we check the layout. We can see that the first component of the layout is initialized and the second is not, which means that the 4 bytes were actually written on the MDT at the beginning of the file. We do support file mirroring with encrypted files. So, of course, if I verify the file initially, it says that the mirrors are different, but after resync, it's happy. We can read from one of the mirrors. The content is fine here. We can write directly to one of the mirrors. And of course, if we verify, then it says there is a mismatch because we haven't synced yet. Okay, so now let's lock the encrypted directory. Without the encryption key, we cannot read or write encrypted files. Obviously, we cannot create new files, even if we use the setstripe, LFS setstripe command. We cannot truncate encrypted files without the encryption key, but we can get access to the metadata information of the file. So here you can see the timestamps, the access rights, the file owner, etc. You can even get access to the striping information, even if you do not have the encryption key. Of course, you can browse the entire Lustre tree without the encryption key, but here, because this is 2.14, remember, we do not encrypt names. And if we try to remove files without the encryption key, it works. So remember that you can remove files and directories without the encryption key. So now let's unlock again the encrypted directory, which means insert the encryption key. We can again read and write to encrypted files. And now I want to mention a specific feature of FSCrypt. So FSCrypt provides protectors, and it gives the ability to change your protector characteristics. So for instance, we can change the passphrase, and it will not change the master key that is associated with this protector, which means that it will not trigger a re-encryption of all the files that are protected with this protector. It will only change the passphrase. And as you can see, it's pretty straightforward. Okay, so last thing I'd like to mention is concurrent access to an encrypted directory. So here I am granting group access to the Vault directory so that every user in the user0 group can access to it. I'm creating a file named mysecret2, and I'm dropping the cache. Now let's switch to a different user. So this is the same node. This user is different, but is part of the same group named user0. And now if we try to open this encrypted file, it worked. It worked without the need for this user to unlock the directory. So please remember, encryption is not an access control mechanism. Once a user unlocks an encrypted directory on a given Lustre client, the encryption key is inserted into the file system keyring, and it is made available to every process and user that is running on this particular Lustre client node. So please make sure that you properly set your access rights or even ACLs on your encrypted files, because really encryption is not an access control mechanism. Okay, so this is the end of this demo. Let me get back to the slides. Okay. So last word about the FSCrypt user space tool is about the add protector to policy command. So this is a specific FSCrypt command. And thanks to the FSCrypt key wrapping mechanism, it's possible to have multiple protectors on the same encrypted directory. For example, two different passphrases would unlock the same encrypted directory. This ability is very useful for different use cases. For instance, if you have different users sharing the same encrypted directory, instead of having them sharing the same password, for instance, they can use their own password, and those two different passwords would unlock the same encrypted directory. It's also very useful in the HPC domain, when you need to access to your encrypted directories via a batch scheduler or a backup tool. In this case, the batch scheduler would have its own protector for the encrypted directory, and you would use that when it needs to unlock the encrypted directory. As you've seen in the demo, any access without the encryption key is impossible, even to ciphertext data. Okay, now let's talk about performance. In our initial benchmarks, we saw a 30 performance drop in sequential write and a 20% performance drop in sequential read. But can we do something about it? In order to answer this question, we run IR benchmarks on the testbed described here. We are interested in file per process, sequential I/O, and want to measure bandwidth performance. So we made some modifications in the way client encryption is implemented in order to test various hypotheses. Here we are comparing different versions of the code. The blue bar is named no encryption, so this is the performance without encryption. The light gray bar is called no bounce. In this version of the code, we use in-place encryption with FSCrypt instead of allocating a new page that is called a bounce page to store ciphertext. The dark gray bar is called void encrypt. This is a hack of the FSCrypt API so that it does not actually encrypt data, but still handles bounce page allocation. And we just copy clear text data inside the bounce pages. And obviously the orange bar that is named full encryption is the normal encryption code as it is available with Lustre 2.14. As you can see from the graph, the most interesting results to compare are bounce and void encrypt. With no bounce, we have a 10% performance drop compared to no encryption. And with void encrypt, we have a 30% performance drop. So no bounce means we encrypt, but we do not proceed to bounce page allocation. And void encrypt means we do not carry out encryption, but we still allocate bounce pages. So it's really bounce page allocation that hurts. So the next move is to leverage Lustre enc pool mechanism initially developed for Kerberos encryption so that bounce pages for client encryption are taken from a pool instead of being allocated for every call to the encryption primitive as it is designed today in FSCrypt. I want to run benchmark with a prototype based on enc pools and see where it goes. Now let's talk about work in progress, that is to say encryption of file and directory names. This work is tracked under LU 13717. Basically, so there are 6 patches pushed so far under this ticket, and they are still undergoing review. This work consists in wiring up LLCrypt API in a light to encrypt and decrypt names. We have to convert from plain text to ciphertext names before sending requests to the MDT. And we have to convert from ciphertext to plain text upon server reply. We have 2 cases to support. Obviously, with the encryption key, we need to present plain text names. But without the encryption key, we need to present base 64 encoded names so that they can still be handled by applications. There are a number of challenges that come with name encryption. The most obvious one is that names are no longer valid path names, not even well-formed strings. And we cannot just encode those binary names and send them to servers and hope that backend file systems would handle that gracefully. For instance, if you have a plain text name that is name max long, when you encode that, the encoded length will exceed name max because every encoding mechanism has its own overhead. For instance, for base 64, we have a 33% overhead. So if you encode the binary names, a name max long binary name, it will be longer than that, and the backend file system will not be able to handle that long name. Hopefully, LDSKFS and ZFS backend file system should be able to handle binary names. So the idea is to encode binary names on the client side and then send them to servers, and on server side, only decode names in the USD layer just before they are handed over to the backend file system. We use a custom encoding to limit overhead to strictly necessary. by just escaping a few critical characters. The other challenges that I'd like to name are LFS seeker, obviously, that will be impacted by name encryption, and of course, metadata performances that we'll have to investigate. To see how name encryption looks like, let's go for a new demo. So let me switch my display again. All right. So this is a new demo to show you this prototype code of name encryption. So again, this demo is run as a regular user, user 0. We are on the same node, CentOS 8.3 node. I have prepared the file system ahead of time, so it's already mounted. It has the same characteristics, 2 MDTs and 2 OSTs. But this time we are running the Lustre master branch plus the 6 patches from LU 13717. So let's unlock an encrypted directory that has been configured already. I am writing a bunch of files and creating directories inside this encrypted directory. We support long names up to 255 characters. We do support hard links with name encryption. We also support symbolic links. So let's have a look at what we created. Here you can see the very long name. You can also see the hard link that has the same inode number as the file. And you can also see the symbolic link. We do support DNE with name encryption. So here I'm creating a directory on MDT index 1. Yes, it's on index 1. And let's migrate this directory to MDT 0. We can see that it was actually migrated. A few words about the security.c extended attribute. So this is the extended attribute that is containing the encryption context. So this is the nonce that I was mentioning earlier. And it's very important to protect this extended attribute from modification. Otherwise, the file would be corrupted and you could not gain access to your encrypted content. So as you can see, it's not possible to modify directly this extended attribute. So now let's lock the private directory. We get rid of the encryption key. And now let's browse the Lustre tree. As you can see, the names are all scrambled. This is base 64 encoding, but all metadata information is still visible in clear text. So the file owner, the permissions, the timestamps, all that remains visible. So let's have a look inside this subdirectory. Here you can see the hard link that we previously created, and also the symbolic link. But because this is just a base 64 encoding of a ciphertext string, it does not point to anywhere useful. We can also have a look at the striping information of this directory. And as you can see, this is the directory that we we migrated to MDT0 when we had the encryption key. Okay. So that's the end of this second demo. So let me get back to the slides. Okay. Release compatibility. How will we make the transition between Lustre 2.14 and the future versions? 2.14 has content encryption only, and future versions will add name encryption. But remember that in-kernel FScript is not capable of handling null encryption for names. So when upgrading from 2.14, you will have two choices. If you need to keep existing encrypted directories, then it means that you must stick with the embedded LLcrypt library. But we strongly urge you to move your encrypted directories to new ones that will re-encrypt everything, and then you will automatically get name encryption. If you do not need to keep existing encrypted directories, then it means that you could directly make use of the in-kernel FScript library. So to conclude, the project roadmap is the following. In 2.14, we delivered content encryption and encryption policies support. And the target for 2.15 is to provide name encryption and performance optimizations. And that's all for this presentation. I hope it will make you want to try encryption and hopefully not against your users well. Thanks. Any questions?
Thank you very much, Sébastien. This is a very good, very nice presentation. Apparently people are very interested in this and they have raised some questions. And let's see, we do have a couple minutes to take the questions. Let's see, some questions already been addressed or answered by people, I think. And at least one of the questions I can answer. That's about will this live demo link to be included in LUG presentation documentation? Yes, I can answer this one. Yes, we have recorded all the presentations in video, and apparently this live demo is included in that video, and we will make it available on LUG website after the meeting. So performance impact, I think you have already addressed that in your presentation very well. So let's go to the next one. What's the next question? Is concurrent access to an unlocked and encrypted directory supported from multiple clients? Can you answer that, Sébastien?
Yeah, so basically the problem with concurrent access is really when you are on the same node. Of course, if you are on different clients, then you do not have this effect due to the encryption key being inserted into the system keyring. So if you are using separate clients, then on each of the clients, you need to unlock the directory, the encrypted directory that you want to access, so that it's the encryption key is loaded into the local node memory.
Okay, I got a new question here. How would access from a batch job work?
So this is really where the ability to use multiple protectors from the same for the same encrypted directory shows its value. So basically, you would, for each directory that you want to encrypt, you would create a protector dedicated to the batch scheduler. So it can be, as I shown in my presentation, it can be a passphrase, but it can also be, for instance, a row key. So maybe this is much more well, it's much more suitable for a batch scheduler, which is not interactive, obviously. And so when you launch your jobs via the batch scheduler has a a pre-stage or in a pre-phase would have to unlock the encrypted directories by itself using its own protector, for instance, its own row key, and then the files could be accessed in plain text.
Okay, a very quick question just received. Will encryption events be recorded for challenge for change logs in the log reader?
So there is not really any encryption events. So maybe, James, I don't know if you're referring to the fact that you lock or unlock a directory. So that's a good question. I haven't looked into that. Maybe that would be good to have that recorded as well. But for now, I guess it's like any other IO control command that you would issue on a file, and I think it's not recorded in the change logs.
Okay, thanks. Thank you again, Sébastien, for this impressive presentation and the very nice live demo.